this lesson will cover de Moivre's theorem. Since we have learned how to multiply complex values, the next logical operation would be to learn how to perform powers and roots of complex values. De Moivre's theorem explains how to raise a complex value to an exponent. And it's surprisingly simplistic. Based off of what we know with multiplication, you have two numbers that you're multiplying together, you multiply their radiuses, or radii, and you add their angle measures. With exponentation, you take your radius and raise it to the nth power. Same thing as multiplying different radii. And you take your theta and you multiply it by n, which would be like adding together multiple times. So we need to make sure the resulting angle measure is within the range of 0 degrees to 360 degrees, or 0 to 2 pi, whichever angle set you're using. And it may be necessary to express the final answer in rectangular form. So let's start off with an example. Evaluate the following and answer in rectangular form. Okay, so it's good to get a picture of what's going on in order to just kind of see things. So I'm going to draw a real and imaginary axis. Whoops, it's not my imaginary one, that's the real one. So real and imaginary. Now the real part of this number is the square root of 3. So I'll go positive root 3 on this axis. The imaginary part is negative I, so I'm going to go down I this way. There's my value, and I'll just sketch it like that. Now, what I'm going to do is I'm going to take this number and raise it to the 4th power. So square root of 3 minus I raised to the 4th power. Before I do that, I want to convert this thing into the trigonometric form. It's going to be much easier. So the trig form. Let's see here. So I have a triangle here. This side of the triangle is the square root of 3. This side is 1. And the if I calculated the radius, right now the radius would be 2. Okay, and I can prove that if you need me to. So the radius being 2, the radius is the x squared plus y squared. We take the square root. So this would be the square root of 1 plus 3, which is 4. So the square root of 4 is 2. So the radius is 2. That's what I was showing. Now, the angle measure. If I divide all sides of this triangle by 2, then this becomes 1. So that puts me on a unit circle. And the one side of the triangle is the square root of 3 over 2. The other side is 1/2. So this type of a triangle, this with the ratio of sides 1 root 3 2, is a 30 60 90 triangle. This angle measure right here, which is opposite the 1/2, is my 30-degree angle, which means the full angle for this, going this way, I'll just do in red just so you can see a different one, would be 330 degrees. Okay, and it's 330 degrees because it's 360 all the way. I've gone 30 already, so just the difference. This right here can be written as 2 CIS 330 degrees to the 4th power. Now, I tend to do my trigonometry with diagrams and drawing triangles and using the ratio of sides. If you're better with formulas and just memorizing individual pieces, you absolutely could work this problem and I'll do it in red because I'm going to erase it. R is the square root of x squared plus y squared. So root 3 squared plus 1 squared, just like we did. Theta is the arctangent of y over x, so -1 over square root of 3. And if you know what angle measure that results in, or if you have your unit circle handy, you can get the angle measure that way. I just tend to be better at learning procedures than memorizing facts. So either way you end up at this point. So no matter how to get there. Now, the next step, de Moivre's theorem says to take the radius 2, raise it to the 4th power, and take the angle measure 330 degrees, multiply it by 4. So 2 to the 4th is 16. 330 times 4, if you get your calculator out, you'll find it's 1,320 degrees. Well, 1,320 degrees is not in our standard range. So if you look for something coterminal to that, and all you would have to do is just take 1,320 minus 360 until you get to something that's within the range that we use. And you will arrive at 240 degrees. So that's my answer. That's my solution right there. That is in trigonometric form. It does want the final answer in rectangular form, but this is the answer. Changing this into into rectangular form is just a matter of using our transformations. So x equals 16 cosine 240 degrees. Y equals 16 sine 240 degrees. And if you have a unit circle handy, you can use that to get these, or if you want to use a right triangle approach, you can use that. I try and use a variety of approaches to help everybody out here. But the cosine is -1/2, so it would be 16 times -1/2, which is -8. Sine of 240 is -√3 over 2. So 16 times the negative square root of 3 over 2 is going to be -8 square root of 3. So that means in rectangular form, √3 minus I to the 4th power is equal to -8 minus 8I √3. So if we had multiplied out 4 different times, this is what we would have arrived at eventually. I think it would have taken significantly more time than going through just 2 conversions from rectangular to trig, then trig to rectangular. All right, let's evaluate the following and answer in rectangular form. So if I have something that's already in trig form, all right, because this is effectively 3 CIS 120 degrees raised to the 4th power. Then I take 3 to the 4th, which is 81, CIS. Then I take 120 times 4, which is 480. And that's not in the range from 0 to 360. So if I take 480 minus 360, I get 120. Strangely enough. That's just a coincidence there. So 81 CIS 120 degrees. Now to convert that into something that is rectangular, then I need to get the x component and the y component. So the x component is going to be 81 cosine 120 degrees, the y component would be 81 sine 120 degrees. So the cosine of 120 degrees, here's 120, the cosine is negative 1/2, so 81 times negative 1/2. The sine of 120 degrees is root 3 over 2, so 81 times the root 3 over 2. So that gives me negative 81 halves and 81 root 3 over 2. So I can effectively say that this right here is negative 81 halves plus 81 root 3 over 2 times I. And again, it doesn't really matter the position of the I in that second term, as long as it's in there somewhere designating that that part is an imaginary part. That's all that really matters. And that's all there is to de Moivre's theorem. But there is another part that comes out of de Moivre's theorem, which allows us to do roots of complex numbers. So, the nth root theorem. We can expand de Moivre's theorem to include roots of complex values, which can be useful in solving equations. So, if we consider the following equation, x cubed equals negative 8. According to the fundamental theorem of algebra, this equation should have 3 solutions. However, standard methods of solving only result in 1, which would be x equals negative 2. Because if we take the cube root of negative 8, it's negative 2. So negative 2 times negative 2 times negative 2 is negative 8. That's the one that we know of. But the fundamental theorem of algebra states that the degree of your polynomial should indicate the number of roots. So there should be 3 solutions. So what are the remaining 2 solutions? To find the missing 2 solutions, we must approach the problem as follows. Since there are no other real numbers that can be cubed, and the result would be 8, we just assume there's no more real numbers here. In fact, you could graph this, and in order to prove that there's no more real numbers, you'd see that there are no more x-intercepts. So we have to assume the remaining zeros are complex, meaning that they have I attached to them in some way. Which means, in order to find the solutions, we need to find solutions of the form RCIS theta raised to the 3rd power is equal to negative 8. So some complex number in trig form. So we just assume they look like this. The only thing that's missing right now is the radius and the theta. Since 8 is technically a complex number, not really technically a complex number, it is a complex number. We just generally think of complex numbers as having the I attached to it somewhere. But real numbers are contained as part of the complex values. So, because of this, we can express it in the RCIS theta format. It would express as 8 CIS 180 degrees. The reason why is if this is my real and this is my imaginary plane, or axis, if I go 8 in the x direction, in the negative x direction, then r is going to be the distance to the origin, which is 8. Theta is going to be this angle measure right here, which is 180 degrees. So this is in fact another way of representing negative 8. So 8 CIS 180 degrees. Perfectly valid. Okay, so we have got a little bit further here. We know how to cube a complex number. We take the radius and cube it. We take the angle measure theta, we multiply it by 3. So that's what I've done on the left-hand side. And then I've replaced negative 8 with 8 CIS 180 degrees. Now we can expand this out to r cubed times the quantity cosine 3 theta plus I sine 3 theta equals 8 times cosine 180 degrees plus I sine 180 degrees. And all I've done is expanded out what the definition of CIS is. CIS is cosine times I sine of whatever angle measure is there. So I've just replaced. It's fine. Which means we can kind of break this up into 3 separate equations. We need to solve each of these. R cubed equals 8. Cosine of 3 theta equals cosine of 180 degrees. Sine of 3 theta equals sine of 180 degrees. The only place where the last 2 equations are satisfied simultaneously are at angle measures that are coterminal with one another. Coterminal angles would look like this. So 3 times an angle measure theta equals 180 degrees. To make something coterminal with that solution, it would be plus 360 times some constant. So you could add 360 to an angle measure, make it coterminal. You could do 360 times 2 if you let that constant be 2, and that would be 720. So an angle measure plus 720 is coterminal. So this is just setting up coterminal angles. Which means that if we solve this for theta, theta would be 180 degrees plus 360 degrees times k divided by 3. So if k is equal to 0, let's see what happens. Well, then theta would be 180 degrees plus 360 degrees times 0 divided by 3. So 360 times 0 is just 0, so effectively it's just 180 divided by 3, or 60 degrees. So that's one value. If k is equal to 1, then theta would be 180 degrees plus 360, 360, not 66, times 1 divided by 3. And this would be 180 plus 360. Or another way I could think of it, if I divided 180 divided by 3 and 360 divided by 3. Either way is fine. So this is effectively, so 180 plus 360 is 540. 540 divided by 3 is 180. If k is equal to 2, and just bear with me here, I'll get to a point of what I'm doing. I'm just showing you that for different values of k, we can get different solutions. So 180 plus 360 times 2, so 180 plus 720, that is. And then that divided by 3 is 300. So it's 900 divided by 3, which is 300 degrees. If k is equal to 3, this would be 180 plus 360 times 3 divided by 3. So 180 plus 360 times 3 is 1260. Divided by 3 is 420. So 1260 divided by 3 is 420. But that's outside of the range of 360, so if I subtract 360 from that, I get 60 degrees again. So I don't get a new angle measure. It's already part of my solution set. And if I continued this process on, if I did k equals 4, 5, 6, and so forth, you'll see the pattern repeating 60, 80, 300, or 60, 180, 300, 60, 180, 300. It would continue to repeat over and over. So the unique solutions here are 60, 80, and 300. So these right here are unique solutions to the problem. And basically what they imply is that the solutions all have the same radius, which is going to be 2. That's kind of a basis. So the 3 solutions that we're looking for will be this: 2 CIS 60 degrees, 2 CIS 180 degrees, and 2 CIS 300 degrees. Okay. Now there's something interesting about this result. Let's graph these solutions. All right, so the solutions I had: 2 CIS 60, 2 CIS 180, 2 CIS 300. So here's a plane to draw them on. All right, now they're all radius 2, which means, you know, I have a circle of radius 2 that they are all going to be located on. So it's really just the angle measure that's changing. Now, 60-degree angle measure would be, so like right here. Okay, so this would be, for instance, 2 CIS 60 degrees. The 180-degree angle measure would be right here. So this would be 2 CIS 180 degrees. And lastly, the 300-degree angle measure would be like right here. So 2 CIS 300 degrees. If you'll notice, this basically takes this circle of whatever our base radius is and divides it into 3 equal portions. And what's interesting about roots of complex numbers is that the solutions will always do this. They'll take a circle. It doesn't have to be a unit circle. It could be of any radius. And the solutions will always divide evenly. So I have an app to kind of help you visualize that. You can try it for different values of your initial complex number and different number of roots. But let me show you it. So let me pull up that applet. Okay, so I have here, I can change the input value. So the input value, let's say, is CIS 30 degrees. And I'm ignoring the radius of the circle. I'm just going to put everything on the unit circle here, just because it doesn't really matter. The radius only comes into play in multiplying all these numbers the same. So then if I hit update, then what it's going to do is it's going to calculate the 3 roots for that particular value. So the 3 roots: CIS 10, CIS 130, and 250. If you'll notice, all 3 of those roots divide that unit circle into 3 equal portions. No matter what your initial number is, let me put it at 90, that will always be the case. All right, and even if you increase the number of roots, so let's say I have 4 roots, then what it does is the solutions equally portion that unit circle based off of your input value. Let me get right at 270. There we go. Now, if we go up to 5, 6, 7, it doesn't really matter. That will always still occur. Here's 7 equal portions of the circle. So basically what that's saying is if you raise any of these to the 7th power, then you're going to end up with this initial input value. So let me go off like 30 degrees, CIS 30. If I take CIS 56, raise it to the 7th power, I'm going to end up with CIS 30. So, and it's interesting that they all equally portion the unit circle in that respect. So in summary, I know that's a lot thrown at you and it seems like it's overwhelming at this point. I understand. The process that you have to follow is actually not that bad. So for any complex value z equals r CIS theta written in trig form, the nth root of z are the nth root of r CIS alpha, where alpha is defined through this formula, theta plus 360 times k divided by n, where k goes from 0 up to 1 less than whatever n is. Because when you get to n and go on, you start getting repeated roots. Okay, so let's try a couple of examples. So let's find all cube roots of 1 plus I root 3 and write your answers in trig form. Alright, so in order to do this, we need to be in trig form to begin with. So 1 plus I root 3, here's my real and imaginary. So 1 on the real, root 3 on the imaginary. It's like right here. So I need to figure out what, I know this x and I know this y. I need to know my r and my theta. So r is equal to the square root of x squared plus y squared. So 1 plus root 3 squared, which is going to be square root of 4, which is 2. Theta is going to be the arctangent of y over x. Oops, yeah, I mixed up my x and my y. Sorry about that. That's confusing. Let me fix that. This is the y value. This is the x value. So the y value is square root of 3. The x value is 1. So if I need to do an arctangent for root 3 over 1, then let me think of this as, say, arctangent of square root of 3 divided by 2 over 1/2. If you have your unit circle handy, then just look for, where sine is root 3 over 2, cosine is 1/2. So that happens at 60 degrees. Or get your calculator out. Just make sure you're in degree mode and do the arctangent of the square root of 3. Your answer is 60. Either way is fine, as long as you're allowed to use that calculator on that portion of the test. So, and refer to your instructor if that may or may not be the case. So the next thing is to express this value, 1 plus I root 3, in trig form. So this in trig form is going to be 2 CIS 60 degrees. Now, what I want to do is I want to find the cube roots of this. So the cube roots are going to be found like this. So the cube roots of 2 CIS some value alpha, where alpha is given as theta plus 360 degrees times k divided by n, for k equals 0, 1, and 2. All right, so I'll say alpha 1 here. The theta is constant, it's 60. Then I'm going to let k equal, let me say alpha sub 0 to get that to mesh up, divided by n, which is 3. So effectively, in this case, it's 60 divided by 3, which is 20 degrees. Okay, there's my first root. So my roots, I have cube root of 2 CIS 20 degrees. Here's one. When k is equal to 1, it's 60 degrees plus 360 degrees times 1 divided by 3. So 60 plus 360, that's 420, divided by 3, that's 140. That's my next angle measure, so it's going to be the cube root of 2, CIS 140 degrees, and the last one, 60 degrees plus 360 degrees, sorry about that, times 2, divided by 3. So 60 plus 720 divided by 3 is 260 degrees. So my last root is the cube root of 2 CIS 260 degrees. And as long as I'm asked to leave those in trig form, there's nothing more I have to do. I'm all finished. All right, last example. Find all solutions to the equation and leave your answers in trigonometric form. So x to the fourth plus I equals 0. Well, in order to solve this, we have to do a little bit of work. It won't be too bad. So initially, we could change this into, say, like x to the fourth equals negative I. Okay? And negative I, well, let me show you why I'm doing this. To solve this, then I would take the fourth root of both sides. So x equals, the fourth root of negative I. So in order to do these fourth roots, I need to change negative I into a complex value in trig form and then apply this nth root theorem. So here's negative I, and it's effectively along 270 degrees. This radius here is going to be 1. So negative I is equal to effectively CIS 270 degrees. All right, now what I need to find is all the fourth roots of r, which r is 1 in this case, CIS some alpha value, and alpha is equal to theta plus 360 degrees times k divided by n, where n is 4, and k goes from 0 to 3 in this case, because k always goes from 0 up to 1 less than the index of your root. So alpha sub 0 is going to be 270 degrees plus 360 degrees times 0 all over 4. Sub 1, 270 plus 360 degrees times 1 all over 4. Alpha sub 2, 270 degrees plus 360 times 2 divided by 4. And the last one we would get from 270 degrees plus 360 degrees times 3 all over 4. Now we need to compute each of these, and I'll let you use your calculator here, but to speed it up here, the a sub 0 becomes 67.5 degrees. The next one is 157.5 degrees, and then 247.5 degrees, and lastly 337.5 degrees. So that my roots, remember r was 1, so we don't have to write in that. So my roots are just CIS 67.5 degrees, CIS 157.5 degrees, CIS 247.5 degrees, and CIS 337.5 degrees. And those are the 4 solutions to that problem. So each one of those, if you raise it to the 4th power, you'll end up with negative I.